Okay everyone, let's go ahead and take a look at chapter number 22, which is applications of the derivative. Now in chapter number 20 and 21 we introduced calculus, starting off with the derivative, and in chapter number 21 we finished off making sure that we could calculate the derivative given any function that we have using the rules for differentiation. So now we're going to take all of that information and we're going to make sure that we can apply it. Now, how do you apply all of that information? Well, we're going to study our three basic means by which we can do that. One is by graphing and analyzing a particular function. So say, for example, if we have this particular function right here, f of x is equal to x squared plus 1 divided by x plus 4, I don't think any of us can visualize what that looks like, but calculus will actually give us a means by which we can graph and analyze that particular function, again using the derivatives. Okay? In addition to that, the calculus and differentiation will also be able to help us look for optimization. So in other words, when we're talking about optimization, we're talking about maximum and minimum values. And we'll go ahead and take a look at that once we get there. Okay. In addition to that, one of the primary focuses for this chapter is going to be looking at the relationship between the distance, velocity, and acceleration. So of course this is a very scientific aspect. And for those of you that are in physics, you understand exactly what the relationship between those are. But we're also going to take a look at it from a very mathematical point of view, because the derivative will be able to allow us to investigate that very easily. So let's go ahead and start taking a look then at this particular section 22a and b, which is called functions involving time. Now, one of the things that we're going to focus on right now is this here with the distance, velocity, and acceleration. Let's just say, for example, that we have what is called a distance function. So in other words, what this function will tell you is, given any particular point in time, how far away are you from the origin, the point of origin. Okay, so let's go ahead and say that we have this particular function, and notice that it's called s of t, and let's just say that it's -1 plus the square root of t. Now, I went ahead and graphed this function, which is a very simple function to graph because we just plot particular values. Notice that I start off at t is equal to 0. If I substitute 0 in there, I get s of 0 equaling -1, and that's why I have this point there. If I substitute the value of t is equal to 1 into that function, I get s of t is equal to s of 1 being equal to 0. And then I chose this point over here because I have the square root, so I said if I let t be equal to 4, the square root of 4 is going to be 2, 2 minus 1 is 1, and that's why I have that point there. So generally speaking, I know that this function is going to go ahead and start curving like that, and so I just went ahead and drew a very nice curve for this particular distance function. Now, one of the things that we're going to have to do, of course, is go ahead and apply some of the derivative concepts and calculus concepts that we have to this particular situation. So let's say, for example, what we want to do is we want to find the average rate of change of the distance with respect to time on the interval from 0 to 4. Now, how do we go about doing that? Now remember, whenever we talk about the average rate of change over a particular interval, what we're really referring to visually is what is the slope of the secant line. So this is going back all the way to chapter number 20. Remember that the average rate of change is the slope of the secant line, which joins the endpoints at when t is equal to 0 and when t is equal to 4. So if we go ahead and take a look at this, we're talking about this particular value here and this particular value here. If I was to go ahead and connect that with a line, which would be the secant line, how would I go about talking about the slope of that? So if I was to go ahead and let's just stop this like this. Okay, there's the secant line. What's the slope of that line? That's what we're talking about when we refer to the average rate of change. Okay, so we know that at s of 0, we have the value of -1 for s. When t is equal to 4, we know that the value of s is going to be equal to 1. So after that, it's just a matter of calculating the slope. So the slope of that secant line is just going to be the change in s over the change in t, right? It's just finding the slope. So this is going to be 1 minus a negative 1 divided by the change in time, which is 4 minus 0. So this is going to be 2 over 4, which is going to be equal to 1/2. So that means that the slope of this secant line is 1/2. That is the average rate of change. Okay? Now, let's go ahead and take a look at what we're referring to when we talk about the instantaneous rate of change. And of course, we cannot talk about an interval. We're going to talk about at a particular instant in time. So let's say, for example, we're looking for the instantaneous rate of change of this particular distance function when t is equal to 1. So what we're talking about is we're talking about at that particular instant, what is the rate of change? So, of course, hopefully all of you are familiar with this. We're talking about the slope of the tangent line. Oops, let's go ahead and write that out. This is the slope of the tangent line when t is equal to 1. So, of course, we're talking about this tangent line here. Okay? What is the slope of that tangent line? Now, we know that if, in order for us to calculate the slope of the tangency, well, we have to take the derivative because that's what the derivative gave us. So if we go ahead and determine the derivative of this original s of t function, then I have s prime of t. Well, I know that the derivative of negative 1 is 0. Now this was the same thing as t to the 1/2 power. So this is going to be 0 plus 1/2 t to the negative 1/2. Okay, so what I have then is s prime of t is going to be 1 over 2t to the 1/2 power. That's the exact same thing as 1 over 2 times the square root of t, and that's what s prime of t will be. So if I go ahead now and calculate what that would be, this would actually be 1 over 2 times the square root of 1. So this is going to be 1 divided by 2, and that will be your instantaneous rate of change at the particular value of this particular function when t is equal to 1. Okay, so it's kind of putting a lot of things back into perspective here, all the way from the beginning in chapter 20, with regards to the concepts that we're dealing with regards to average rate of change and instantaneous rate of change. How the average rate of change is related to the secant and the slope of the secant line, and how the instantaneous rate of change is related to the tangent line and the slope of the tangent line. Okay? And that's all we're going to be looking at right now, is we're going to look at how to deal with functions involving time and applying our concepts as well as our skills with regards to calculus. Okay, so give it your best shot. We'll see how everybody does with section 22A and 22B. All right, see you next time. Cheerio.